Hello everyone, myself Madhuri Modak, Assistant Professor in Mathematics, Department of Computer Science, Abhidayananvar Senior College. In the subject Mathematics, Groups and Coding Theory is very important paper. Now in Groups and Coding Theory, already we have seen the first unit. Now we start with the second unit, that is Groups. Now we will see the definition of group. Now, after defining commutative, associative, identity element and inverse of every element, it is possible to define group. Let G be a non-empty set together with an operation star, usually called multiplication. We say that G is a group under the operation star if the following four properties are satisfied. Now, first property is binary operation or closure property. The operation star is a binary operation on G, that is, to each ordered pair AB, the element A star B is a unique element in G. In this case, we say that G is closed under star. So already we have seen all these properties, just we are collecting all of them together. So first, star is binary operation. Secondly, star is associative. Then third is there is an element E in G, that is identity element. And fourth, for every element A in G, there is some element B in G called its inverse. So if all these four properties are satisfied, that is star is binary operation, star is associative, identity element is existing in that set, and for every element in G, there is an inverse. Then we say that G is a group with respect to star. Now see some remarks. If a group has the commutative property, that is A star B equal to B star A for every pair of elements A, B, then we say that the group is abelian or commutative group. It means all the properties of group are already satisfied, and together with these four properties, group is satisfying commutative property, that is A star B equal to B star A for all A, B in G. Then we say that that group is an abelian group or commutative group. Now when we say that a group is non-abelian, if there is some pair of elements A and B in G for which A star B not equal to B star A, because if for at least one pair of elements A and B in G, we are getting A star B not equal to B star A, then in that case commutative property fails, and in that case the group is non-abelian. Now, whenever in a group G, if A is an element of G with inverse B, then B is an inverse of A. So, if A is an inverse of B, then obviously B is an inverse of A. Now, see some examples which are very clear. The set of integers Z, the set of rational numbers Q, and a set of real numbers R are all groups under ordinary addition. That is, with respect to usual addition of numbers n, not n, with respect to usual addition of numbers Z, Q and R, all are groups, because in each case 0 is the identity element. For every element A in that set, minus A is its inverse. Addition is a binary operation. Addition is associative. So all these properties are satisfied by these sets with respect to addition. So these are groups. But remember, in case of Z, Q and R with respect to addition, 0 is the identity element. And for every element A in that set, its inverse is minus A, which is known as additive inverse of that element. Now, second example, the set of integers Z under ordinary multiplication is not a group. Now, to show that some set is a group, it must satisfy all the four properties. But if one of the property fails, then in that case, immediately we can say that it is not a group. And remaining properties we can skip. Now here the set Z under multiplication is not a group. Actually, for any element A in Z, A into 1 is A. So 1 is the identity with respect to multiplication. But To find its inverse, we need to find some element b such that a into b is equal to 1. Then b will be inverse of a. But ab equal to 1 gives b equal to 1 upon a, and 1 upon a is not an integer always. For example, if we consider a is equal to 7 and its inverse as b, then 7b must be 1. But then b will be 1 by 7, and 1 by 7 is not an integer. So inverse does not exist for every element of z with respect to multiplication. So it is not a group. Then the set Q plus of positive rational numbers is a group under ordinary multiplication. Multiplication of any two positive rational numbers is again a positive rational numbers. Then multiplication is associative. Also, 1 is the identity element and inverse of any element a in Q plus is 1 upon a. Similarly, R plus with respect to ordinary multiplication is a group with 1 as identity element and inverse of a as 1 upon a. Then consider Q star, Q minus 0, that is set of non-zero rational numbers. Again, this is a group under ordinary multiplication with identity 1 and inverse of a as 1 upon a. Same for R star, that is non-zero real numbers. 1 as identity, and for every element a in R star, 1 upon a is its inverse. Now see, m n by n r, that is set of all n by n matrices with real entries. Now under matrix multiplication, that is multiplication of two matrices, it is not a group. Actually, for any two n by n matrices with real entries, their multiplication is again an n by n matrix with real entries. So it is a binary operation. Also, multiplication of matrices is associative. So that also holds. So binary operation and associative, both the properties are satisfied by m n by n r. Then what is the identity element for any matrix A in m n by n r? There exists identity matrix In of order n by n such that A into In is equal to In into A is equal to A. So identity matrix of order n means n rows, n columns with all diagonal entries 1 and non-diagonal entries 0, that forms an identity element of m n by n r with respect to multiplication. But for inverse of some matrix A in m n by n r, there must exist B such that AB equal to BA is equal to IN. But every matrix does not have inverse. Inverse exists only if it is a non-singular matrix. That means determinant is not equal to 0. So there are some n by n matrices without inverse. For example, if I consider any 0 matrix, then its determinant is 0. So it doesn't have inverse. Hence, m n by n r, that is set of all n by n matrices with real entries, it does not form a group with respect to matrix multiplication because property of inverse fails here. Now, the set of all 2 by 2 matrices with real entries is a group under component-wise addition. Or the same question can be asked as m equal to a, b, c, d, where a, b, c, d are real numbers. It means it is set of all 2 by 2 matrices with real entries. It forms a group with respect to matrix addition. So to show that it is a group, we have to show that addition is a binary operation on M. It is associative. Then we have to find identity element, and then we have to show that inverse exists for every element of M. Now to show that it is a binary operation, we consider two elements, say A and B, in M. As matrices are denoted by capital letters, here we are taking A and B as capital. So these are two matrices from M with real entries. Now A plus B, as it is component wise addition, we add first row first column element with first row first column element of second matrix. So A plus E. Similar way, component wise addition gives us B plus F, C plus G and D plus H. as all are real numbers and addition of real numbers is again a real number, we get this is a 2 by 2 matrix with real entries and hence it is a member of M. So we can say that matrix addition is a binary operation on M. Now to prove associativity, we consider A, B, C as three matrices from M. Now we find A plus B plus C. So first we add B and C. So according to matrix addition, we get this matrix. Again do the matrix addition. So in A, we are adding here E plus I. In B, we are adding F plus Z. Now it's all are real numbers and in the real numbers, matrix addition is associative in every element. By using associativity of addition, we write this as A plus E plus I. Again, B plus F plus J and so on. Now, we have to show that this is equal to A plus B plus C. So, we separate every addition by forming two matrices. One by taking all elements from first bracket and another matrix by taking second element. So this is equal to A plus E, B plus F, C plus G, D plus H plus I, J, K, L. Again by splitting addition into two matrices, this is ABCD plus EFGH plus this matrix remain same. Now this is A, this is B and this is C. So finally it is A plus B plus C. So starting with A plus in bracket B plus C, finally we got it is equal to A plus B plus C. So matrix addition is associative in M. Now think of identity element. So according to definition of identity, for every element in that M, means for every 2 by 2 matrix say A, B, C, D in M, we must find some 2 by 2 matrix say E such that A plus E is equal to A. So as we are doing it as component wise addition, to get the same element in every element of that matrix, we must add 0. So what is the identity element? It is nothing but 0 matrix of order 2 by 2, because in A, if we add 0, 0, 0 matrix, then we get the matrix A itself. So 0 matrix of order 2 acts as identity with respect to matrix addition. Now the last property is inverse. So for every A in M, we have to find some matrix B such that A plus B equal to B plus A is equal to identity element, that is 0 matrix. So in that matrix A, B, C, D, we have to add some matrix so that the right side matrix is 0, 0, 0, 0. So in this A, if we add minus A, then only we get 0. Same way in B, if we add minus B, then only we get that element as 0. So for matrix A equal to A, B, C, D, we must add minus A, minus B, minus C, minus D. Then only A plus minus A is equal to minus A plus A is equal to 0 matrix, which is identity. So for every matrix A, minus A acts as inverse of A with respect to matrix addition. Thus, matrix addition is a binary operation on M. Then it is associative. 0 matrix is the identity element and for every element in M, minus A is its inverse. So M forms a group with respect to. Now already we have seen the definition of group. A non-empty set G together with a binary operation star is a group. If star is associative in that group, identity element exists and inverse exists for every element. Now see the next example. Define a binary operation star on Z as follows. A star B equal to A plus B minus 3, where A, B belong to Z, means A and B are integers. Show that Z is an abelian group. Now first we show that Z is a group. Now to prove that it is a group, we show that star is binary operation, star is associative on Z, identity element exists and inverse exists for every element in Z. Actually, we can skip the part of showing star as a binary operation on Z because already it is given. But as a practice, we show that star is binary operation on Z. Now see the definition of star. For AB belonging to Z, A star B is A plus B minus 3. Means while finding A star B, we are adding first element A in second element B minus 3. For example, 2 star 5 will be 2 plus 5 minus 3. In this way, you can find A star B. Now, to show that a star is a binary operation on Z, we have to show that for any two element A, B in Z, A star B is again a unique element of Z. Now, for that, consider A star B, which is A plus B minus 3. Now, A and B both are integers, so their addition is again an integer. And that addition minus 3 is always an integer, and this answer is unique. So, star is a binary operation on Z. Now, to prove associativity, we take three elements A, B, C from Z, and then we find RHS and LHS separately. Now, A star in bracket B star C. Now, applying the definition of star for B and C in bracket, we get A star B plus C minus 3. Now, again applying the definition of star, we get A as first element and consider B plus C minus 3 as B in the definition. So, A plus B plus C minus 3 minus 3. So, it is A plus B plus C minus 6. Now, another side is A star B star C. Now, using the definition of star in first bracket, this is A plus B minus 3 star C. Now, it is equal to first element A plus B minus 3 plus C minus 3, that is A plus B plus C minus 6. Now, observe the RHS of 1 and 2, both are same. Hence, in general, for all ABC in Z, we get A star B star C is equal to A star B star C. Hence, star is associative. Now, third is finding the identity element. So, we consider E as identity element in Z with respect to star. By definition of identity, A star E is equal to E star A is A. Now, as it is commutative, A star E equal to E star A. So, directly compare A star E with A. Now, by definition of star, A star E is A plus E minus 3. So, we get A plus E minus 3 is A. Now, shifting A on right side, A minus 8 is 0. Again, shifting 3 on right side, we get E equal to 3. So, 3 is identity element in Z with respect to star. Now, it is possible to find inverse for every element. Let A belong to Z and B belong to Z be inverse of A in Z with respect to star. Again, by using definition of inverse, we get A star B equal to B star A is equal to identity. So, consider A star B is identity. Now, identity is 3 in this case. So, putting the value A star B equal to E implies A plus B minus 3 equal to 3. Here we have used definition of star and value of E is 3. So, solving for B, we get B equal to 6 minus A. So, if A is any element of Z, then 6 minus A is its inverse. For example, if I consider A is 2, then 6 minus 2, 4 is inverse of 2. So, in this way, we can find inverse for every element. Thus, all the four properties are group are satisfied. So, Z forms a group with respect to star. Now, in question, we have to show that Z is an abelian group. So, we show star is commutative also. So, one more property we have to check in this case, that is commutative property. So, we take two element A, B in Z and we show that A star B equal to B star A. So, A star B is A plus B minus 3 by definition and B star A is B plus A minus 3. But addition is commutative in Z. So, B plus A is same as A plus B. So, we get A star B equal to B star A. That means star is commutative in Z. And Z forms an abelian group with respect to star. Now, one more example about matrices. Now, here we are considering the set GL2R. It is set of all 2 by 2 matrices ABCD, where ABCD are real numbers and AD minus BC is not equal to 0. What is AD minus BC? AD minus BC is nothing but determinant of this 2 by 2 matrix ABCD. So we are considering GL2R as set of all 2 by 2 matrices with real entries whose determinant is not equal to 0. Now we have to show that this is a non-abelian group under matrix multiplication. Now this is a special group which is known as general linear group of 2 by 2 matrices over R. That's why the notation is GL2R. Now to show that it is a group, first property is binary operations. We consider two elements from GL to R, which is A and B. Both are 2 by 2 matrices with real entries. And for first matrix, AD minus BC is non-zero, and for second, EH minus GF is not equal to 0. In other words, determinant A is non-zero, determinant B is non-zero. Now to show that their multiplication is an element of GL to R, we have to show that A multiplied by B is a 2 by 2 matrix with real entries and determinant is not equal to 0. Now consider first A multiplied by B. Now by matrix multiplication we get this as 2 by 2 matrix. And as all are real numbers, their multiplication and addition is again a real numbers. So A into B is a 2 by 2 matrix with real entries. Now the only thing remaining is determinant of this A into B must be non-zero. Now by property of determinant, determinant of A into B is equal to determinant A into determinant B. But as A and B are members of GL2R, both the determinants are non-zero. So this product is also non-zero. Hence A into B is a 2 by 2 matrix with real entries and its determinant is non-zero. So A into B is in GL2R. So for any two members of GL2R, their matrix multiplication is again in GL2R. So it is a binary operation on GL2R. Now second property is associative property. For that we need three elements of GL2R. So we consider here A, B, C as three matrices of GL2R, and we show that A multiplied by BC is same as AB into C. Now first consider A into BC. So this is A. Now B into C. This is product of B and C. Now do this multiplication. So by multiplication of matrices we get this matrix. Now using distributive property of multiplication over addition we get this matrix. Now we consider this as equation number 2. Now we find another side separately as AB multiplied by C and we follow the same procedure. Now see this matrix and previous matrix. So comparing these two matrices we get A into BC is equal to AB into C. So matrix multiplication is associative in GL2R. Now the third property is identity element. So here if we consider any matrix A in GL2R, then there exists identity matrix of order 2 by 2 such that A into I is equal to I into A is equal to A. Hence, identity matrix of order 2 by 2 is an identity element in GL2R with respect to matrix multiplication. Now, inverse. Remember, for this matrix, this is an inverse. For A equal to ABCD in GL2R, we get this matrix say B such that AB equal to BA is equal to identity matrix. So this is the inverse of matrix A equal to ABCD. Thus all the four properties of group are satisfied. So GL2R is a group under matrix multiplication. We have to show that it is a non-abelian group. So we show that multiplication is not commutative in GL2R. Now as we have to show that it is not commutative, it is enough to take specific matrices A and B for which A into B is not equal to B into A. So you can give any example for which A, B and B are different. So here I have taken A as 2, 3, 4, 10 and B as 5, 1, 3, 2. Now both are members of GL2R because both are 2 by 2 matrices with real entries. Then here its determinant of A is 20 minus 12, that is 8, which is non-zero, and for B 10 minus 3, that is 7. So both are non-zero. Thus we have taken A and B as 2 by 2 real matrices with non-zero determinant. Now by doing matrix multiplication we get AB as this matrix and B as this one. But by equality of matrices AB is not equal to BA. So matrix multiplication is not commutative in GL2R. So GL2R is a non-abelian group under matrix.